now we see, okay, what we are doing at working, we hope that a red line or lila line goes under blue line, and then it means we found solution. So it's our main hope. And we will see in flow simulations looks much more interesting. There are many lines you can check. So we see now it's good direction, yes. And it's difficult to find first solution. Yes, if you found first solution, then it's easy to find second solution with more preload. Okay, please, yes, say from Felix and then start the simulation. And then you will see same result. Okay, you did it with good measurement. No, this is a yes, this is result. But this result for time step, look, now it's time 0.8. Means result for 0.8. You don't have pressure in 0.8. Yes, you have only, for example, you can show results at 0.7 seconds. It means
doesn't work on laptop.
only preload with
Yeah.
5.
It would exceed the number of limits allowed by free license software if you try to simulate it.
For example,
I'm pausing, remember.
what's happened if program makes, I don't know, 20 iterations and didn't find solutions, then program say red line and say 0.455, it's too much for this step, and try to do, for example, 0.5 seconds, yes? Not so much low. Yes, do you understand? It means it's not possible to calculate from 8 kilonewton. Yes, program try to calculate, for example, first 1 kilonewton, then 2 kilonewton, 3 kilonewton, yes? So, or for example, program tried to calculate 8 kilonewton and then say, oh, it's too much, and program tried 4, then 2, then 1, then 0.1 maybe. So it means it's always iterative process. And you see now, yes, I found solution 0.75, and now this program tried to find 0.05, and we see it looks very good. Okay. And we can check results. So then we need to answer the question, breaks our part or not, yes? So, but before we answer this question, we will try to do this simulation quickly. So, okay, now we need, of course, to wait. We have to wait, and okay, now first step finished, and then comes second step, and then we have to wait, and then we can show how much time we need for this simulation. Yes. So, for example, we can also it's not important to know, but we can also show how much time it costs during calculation. I can open here by solution Opal server file directory, and here I can find everything. For example, with this function, I can check my methods. Is it quickly now or slowly? For example, here I can find I have many files, and here I have file monitor, for example. If I open this file, then I see exactly how much time I need for every iteration for this editor. So then I see, for example, first convergent iteration, 8 iteration, I need 150 seconds, yes? And then, for example, first load step, sub-step 7, yes, iteration 15. I found solution for 1 second, and it cost me 370 seconds, yes? And then we will see, for example, then it's not important to wait until full simulation, yes, completed. I can see, we will see now, yes, if I change something, it will be quickly or slowly with this changing. So, for example, I can change method for contact, or I can change some algorithm, and then I see exactly here result. Okay. And this is the main field, yes, what we are watching always. And we see, yes, program tried to calculate 1.2, it means now we have pressure. 0.2 pressure, it means 5 bar, megapascal, it means 1 megapascal. Try to calculate now program. So press stress is finished. We can check results. 1 second result. Yes, it's full press stress finished. It looks very good. Now comes pressure and try to destroy this part, this connection. So now we found solution 0.2 and okay, and now we will use our theoretic knowledge to be quickly. So okay, before we answer the last question, yes, for what we are doing simulation? We are doing simulation only to answer the question, mechanical simulation breaks our part or not? So this question we have to answer. And if breaks, after how many loads? Yes, how many loads? For example, it works like customer give us information, this part have to work 150,000 times with so much pressure, yes, and we have to check it. So, and then we simulate it and we try to do that with same safety, I don't know, 20%, 50% safety works 150,000 times. Yeah, then we are doing tests, and tests is nothing broken, and then it's everything okay. Then everybody is happy, simulation say it's okay, measurements told it's okay, and then is everything okay. So, okay. And we see now, okay, it's need a lot of time, of course, yes, now, yes, we have contacts, we have bad meshing, it's also need a lot of time. With a good meshing, you will be quickly, and you will get much more beautiful here results. We will see now how looks results here. It looks not so really fine, not so really beautiful, yes, I mean, it's not so beautiful, yes. Normally it have to be, I don't know. So you see this, how it's called, how colors goes from red to blue. So not like in some points it's red, some points blue and green, and it shows us that mesh is really bad. And it's not so really exactly this simulation. So okay, now program try to calculate 2 second. 2 second step, and then program finished and everything is okay. Yes, program found solution. So program found solution, we have solution, and we see how much the maximum stress and where is the dangerous place. So dangerous place is, now it's interesting. Okay, now we have results. Okay, we need to wait. Results looks not so good. I mean, our meshing is not so good, but if you make now hexa mesh, you will see much more beautiful results. Okay, simulation is finished. Okay, this I cannot see here results. Yes, now we see only last calculation here time. Yes, well, we need normally solution to see results. Insert stress equivalent stress. This is our main parameter to control. Stress equivalent stress evaluate, and then we will see all results. All results here. Yes. So okay, we see our stress. We see where is the maximum. Yes. We can show maximum stress, and maximum is here. Yes. And you see how it looks with tetra mesh. Yes. It looks really bad. So it looks like I have very bad meshing. Okay, this place is dangerous, yes, and I have only 2 elements in this place, and it's bad, yes. I need to refine this mesh place, yes. And if I do it now with tetra mesh, then I have 300,000 knots. And then I need to wait 2 hours to get good results, also correct results, but 3 hours. And you will get with hexa mesh in 8 minutes maybe good results. So this is a problem, but I see where is the dangerous place, and I see, okay, 290 megapascal is maximum stress. But you will see with tetra mesh, with hexa mesh, you will see here 320 or I don't know. So much more stress, yes? So, okay, our simulation is finished. Yes, it's okay. We can see results, and we can check with this automatic scale, is it everything okay? Yes, it's okay. Yes, you see everything good. And the question is, breaks our part or not? So first, what we need to understand that only tensile stress break parts, break our material. So, for example, you will see it also in examination. This question, I can do it like if I make a little bit maybe more press stress, I will get here red place. Maximum program show me here by not. For example, I can show if I show results not for 5 megapascal but for 1 megapascal maybe, then I will see that the biggest stress is here. Yes, but this place is nothing. Yes, this bolt is always how it called? It's not tensile stress. Yes, not tensile stress. It's press stress. Yes, press stress, break stress make nothing. Yes, for parts. So it's not dangerous. Dangerous is tensile stress. So and here, for example, with if I check, for example, 1.7 seconds, yes, then I have maximum here, but this maximum is not interesting for me. My tensile stress, I can see it also in scaled results, yes? So I see exactly that here I press and here I pull, yes, my material. And this place has tensile stress, and tensile stress breaks parts, yes? And this place is dangerous, yes? And it's not now important that this place has less stress as this, yes? So what is important, I can, for example, show only this part, separate results, stress equivalent, and then I will see where in this class, which place is dangerous. I see this place is dangerous, yes? And for every time step, for 1.7, also this place. Yeah, this place destroyed our part. This is the most dangerous place. So I have the biggest tensile stress in this place. So I can also for presentation I can show only radius. Yes, here is the most dangerous place. I can show stress only on radius. Yes, for example, the presentation you see exactly radius has has stress maximum. Yes, 249. For 2 seconds, it means for 5 megapascal. For example, for 3 megapascal, it's 200. Yes. So it means, for example, if customer told us, is it breaks, and then we can say, okay, with 4 megapascal pressure, it's safe. Yes. But with 5 megapascal, it breaks. So, okay, how we can now say it breaks or this or not? This we are doing later. Now what's important, I want to show how we can use our theoretic knowledge, yes? So, now we calculated this task for 10 minutes, 11 minutes, yes, about. So, and what program did? This is very interesting. We can see what the program did, yes? With solution solver output, we can check which kind of method program used. So, and it will be interesting. You will see which kind of method used the program, and we will see this method. You can find also this information in the lectures, yes. I hope. Or I know we did it before, I think, or we did it before. Oh no, maybe I don't have this in lectures. But okay, we can see the method the program used. Yes, I didn't add it in lectures. Look what kind of method program used. We see preconditioned conjugate gradient solver. So it means gradient solver conjugate. It means iterative solver. So this is iterative solver. So it means program used iterative solver, convergence tolerance, okay, 10 minus 8. Program used this solver. So, and we can see maximum iteration. Yes, it means after this part, program say no solution. So, okay, program used iterative solver But if we show meshing, we have only 60,000 nodes. 60,000. It means I told you about 100 and 300,000. It's direct have to be better. Yes, method. But program decided with very not so big nodes. Decided for iterative solver. Yes, it's not so good. We think. Yes, we think it's a mistake of ANSYS. Okay, it's not guarantee. Yes, it's 60,000 nodes is 60,000 multiplied with 3, x, y, z direction. It means 200,000 system equations. Yes, and about until 500 is direct bet. Yeah, nobody know how much. Yes, for every task is different. But normally, if my nodes, for example, less than 100, 200 nodes, then direct is quickly. And we want to check it first. How I can use my theoretic knowledge now in ANSYS? We can use everything. ANSYS allows everything. It's everything allowed. I can do duplicate, and now I will say to program, okay, now I want to calculate this with direct method. Yes, it's not better. Direct, it's more exactly. Yes, like exactly. It's a wrong word. It's same result. Yes, direct is exactly. Iterative makes with iterative error, but iterative error is 10 in the power of minus 8. Yes, it's also exact. So it means now we are speaking only about time. Yes, same results we will get, and I try to do it with direct solver. Yes, I think 60,000 nodes. It's normally with hexamesh we will get so many nodes. It's better with direct solver to calculate. And now we can say to program exactly, okay, please calculate it with direct method. So for small system, maybe it's better. Okay, how I can say it in ANSYS? I can say everything in ANSYS, and here by analysis setting, you can check analysis setting. We will see many things, and many things called program controlled, yes, program controlled, everything program controlled. But now we will see, okay, solver type, we will change with quick menu, for example, yes, direct iterative. So there are many methods inside direct iterative, but here is main choose. You can choose so main parameter. If you want to choose more exactly, then you can write with this programming where we write RS6 nodes, and you can choose exactly what you want. But here we can choose between two big groups of methods. So we say now direct. So we think it has to be direct better. And then we start simulation again. Okay, solve. And you have to do it also in your practical work. And we will see what's happened. So, and now we will see here the program calculated with exactly with direct method. So, where we can find it? We can find it in where do we change the direct? Here by analysis setting, where we say RS6 node or steps, number of steps. Here we can say solver controls, ledge deflection on, and here we have solver type, direct. It means this theory between direct and iterative methods to solution of system of linear equations. So, and okay, and we can find now in our file solver output also the program uses direct method. So where is it? It is in okay, now it's not so easy. Okay, update interval maybe 50 seconds, and we don't have update. Yes, this point update interval means how often program makes update of information. We say 100 seconds we want to check something, and we can check without changing. Yes, and you see here, for example, yes, the program use sparse matrix direct solver. Sparse means that the zero multiplication with zero elements. It's like modification of this Gauss method. Modification that uses this zero multiplication. Yes, we don't need to do zero multiplication. So our matrix has many zero elements, and then special direct solver try to solve it. And then, okay, we can switch back to 3 or how much second. And then we can see convergence, and we will check is it quickly or not. So, okay, it's also possible that iterative quickly, yes? So it's no guarantee. If I have 10,000 nodes, then I have guarantee that it's direct beta. But with 60,000 also, normally it's also direct beta. And with this strategy, we can save a lot of time. So, we can check, of course, this, what? We can check this monitor file to see this first time step was quickly or not so quick. File monitor here. Okay, but I don't know how long it was in the other simulation. So, but I want to show you some examples with a big task, like, okay, you can find in the lecture also, that, for example, for the big simulation with many parts and stress, press stress, and then, okay, so big simulation needs, for example, normally 45 hours it was, and only with this, when this switching to, no, okay, it was later. We will do it now in other direction. Look, without direct method was 19 hours, 19 and a half, and only with 1 point switching to direct, we calculated this task for 11 hours. So it means 8 hours quickly, like 40% quickly, only with 1 point direct. So, and with second point, we saved 20 hours more. So it means with 2 theory questions, we saved now simulation we did not for 45 hours, but for 11 hours. Yes, with two switching. So we switched to two places in ANSYS, and then we saved 30 hours. Yes, so okay. And this example also same story. Yes, it was with old PC. I don't know why. It was 19 minutes, and with direct method. Okay, here you can find, of course. Yes, here you can find it. Information, what it means, iterative or direct. Program control was iterative and 19 minutes, and with direct, yes, we calculated it for 8 minutes. I calculated this example. Yes, maybe now it will be different with the other meshing, but we will see now. Okay. Okay, now we will check, is it quickly or not? This is the first thing. And second thing, also very important, we spoke about these basis functions, yes? Basis functions, many people forget it, that we have this basis function for interpolation, yes? That every element is interpolated inside with these basis functions, yes? So, and only one rule, define it exactly, yes? And you understand, you need to refine places where you need solution, yes? And with this idea, we can say we need better basis function in the places where we need solution, and not so good basis functions in the places where we don't need solution, yes? For example, ANSYS has linear and quadratic. I can say here I need solution, simple idea. Then I need here quadratic. And other parts, I don't need exactly solution, and I don't need quadratic. I can say it's linear, yes? And then I will be much more quickly without to lose my my results. So, and it's also possible, it's interesting that for this point, ANSYS also has field by meshing, and we saw it before, yes? Element order, program control. What is the program control? Program control is normally not so good. So, program control is not so good. Why? I can show now by statistic, I think, yes. Not statistic, but it was by cannot do now. Yes, it's here quality. I can show what exactly of type of elements program uses. So, and then we will see that program control is like in first lecture, it's normally quadratic for everything. Yes, quadratic interpolation for all parts. So, and we say it's not so good. I don't want to have so fine solution now, for example, for this part, yes, or for this part, I don't need exact solution. Also, if you do now this sweep method, yes, we divide this part, yes, and then we have here hexamesh. For example, with 18 version ANSYS, it was not possible. It was only possible if I divide my part, the program understands it as one part, yes. I divide it only for program to be quickly, for hexamesh. And for example, it was only possible if I say here quadratic, then other parts have to be quadratic. But now, for example, new version, we can say only this radius quadratic and other parts linear. It's also much more quickly, yes? Did you understand the idea? Yes, we make everything what's possible to save time, yes? So, for example, program control, programs say quadratic, but we say now, no, please, everything what we don't need, it's linear. Okay, and now we are waiting till this part. It's interesting, it will be quickly or not. And then we change this, I show you how we can change it to say exactly here linear, here quadratic, and then we answer the last important questions, breaks our part or not. So, okay. And works, everybody started simulation. And there are many points of how we can use theory to be quick. Yes. So, for example, second place. I don't know. I don't have it in lectures, but I have this presentation. Yes, it was for one conference. Second point we didn't speak about it. This line search. So line search is how we calculate the system of nonlinear equations. So it's also one theory question. So, for example, program makes line search program control. Yes, line search program control is also bad. So, if you understand what it means, line search, then you can check. Okay, this story we skipped the drop. It was the last version. Now it calls normal linear quadratic. Yes. So it means I didn't show. Okay, this line search is one theory question, so a little bit difficult as direct iterative, but it's also possible to see results and to say, do you need this line search or not? So, for example, if in this situation I can say I don't need line search, and then now I have 8 minutes, and if I say line search off, then I say 6 minutes 50 seconds. Yes, I saved also, I don't know, 20%. So only with one theory question more. So for the same results. Okay, and now we will see how much time we need with direct method, and it will be interesting. Okay, first simulation we did 10 minutes, I think it was. Maybe now it will be also 10 minutes, why not? But we will see it now. And you have to do it in your practical work, yes, to check it. Is it quickly or not? But okay, 70,000 I have. How much?
When are you gonna pass the practice?
Okay, it means only how we can use our theory to be quick. So 60,000 knots. Okay, and we see now results. And how much time we need. And then we change the last thing. Yes, we say that we want to calculate only linear, only quadratic, only one part where we need. Yes, this radius we want to calculate quadratic. And the other parts we can say linear. Okay, now it's finished. I hope next iteration to 24 iterations, 24 system of linear equations we calculated to find the solution. And everything green, everything okay. Normally we have many red lines, something wrong, but here is a simple example, but it's also a real example. We have very often this example to say some connection breaks or not. Okay, now we finished, and how much time we used for this simulation? And this simulation we did, okay, 12 minutes, yes? Do you see it slowly? Maybe tetramesh. Normally, all examples what I showed was with hexamesh, but tetramesh, look, or this example, and maybe in your hexamesh it will be maybe quickly, but now it's slowly, yes? For example, here it was twice quickly or 3 times quickly, yes? Twice, 2 times quickly. And in this example it was also, yes, like 40% quickly, but maybe it depends on many points, yes, how many iterations we need and so on. But okay, it was slowly, and then the last point will be 100% quickly. I make again duplicate first simulation, and we will say, okay, iterative solver was quickly, yes, we stay with iterative, no problem. But what we doing? We say now exactly the quadratic for radius and linear for other points. It will be quickly.
Professor, when
What?
when you gonna pass the final work? Or
Best what?
when you gonna tell the final work, final report that is it?
Final report. You can find in 1 day before examination is okay. Yes, 2 days, 1 day. But you can find in lectures. It's until I think I wrote it, but it's not 28 January. Yes, it will be Dienstag. Yes, but you can also you have to write a report with screenshots. Yes, you have to do this. You can find in Felix what you have to do. Yes, these 4 tasks: 2 manual, 2 simulations. Report. Yes. So, and if you do it, you will understand simulation. You will answer every question by examination. Okay. Before we make pause. Okay, I duplicated how I can say to program. I want to have exactly, for example, radius quadratic. Basis function and other parts linear. It will be much more quickly. It will be quickly without thinking. Yes, of course I have less nodes. Now I have, for example, here I have 63,000 nodes, and now I say, look, I can say exactly for every part what I want to do. How I can do it very easy. I can say first mesh. Here, not program control, element order, but I can say linear. It means everything is linear now. So, not quadratic. Program control means often automatic quadratic. Sometimes makes linear, but automatic quadratic normally. And then I can say exactly for the part where I have maximum stress, I can do next thing. Look what I'm doing. I'm choose this part. If you make this sweep method, you will see it automatically this point, concrete for every part. But here I can say insert method, and if I choose method, yes, okay, now I cannot do sweep. I can say tetrahedrons. It is tetrahedrons, but I say again tetrahedrons. Yes. So, but here if I do it, I have element order. Yes, and I can say quadratic. Yes. I say here method tetrahedrons, yes? Okay, it's tetrahedrons, but I can say method. And then I say quadratic. And what's happened? Now program makes everything linear, and only this one part will be quadratic. And you can say only your radius will be quadratic. And then I have not 67,000 but 51. And it is of course much more quickly, we'll see now. Okay, now we can make pause. Yes, and then we answer the last question. Breaks our part or not? And then we can start with flow simulation. Okay, I start now and we will see what's happening. Okay, and you can also start. Okay, method to trade runs, and then you can say exactly only this part quadratic. Or you can choose your sweep part, and in sweep part you will find this field element order. Then you can say exactly. And this is everything what is the power of ANSYS. Yes, why many companies use ANSYS. Yes, we have a lot of possibility to be quickly, yes. It's exactly. But we, of course, it's not so easy to use it.